Yeah, good morning.
Good morning, sir.
Yeah. Let's resume our discussion. So before I start, I suggest some of you to mention some of the aspects that we have discussed in last class. So can some of you bring some of the aspects that we have discussed in the last class?
Sir, we discussed about template matching and the numerical complexity involved in it. And we discussed about algorithms that can do work.
Right. So one aspect that we have discussed is about template matching. Okay. And then the complexity involved, fine. So why did we discuss about template matching at all? So any other points that we have discussed in the last class?
To count the errors, sir.
Okay. Please go ahead. Yeah, quickly.
Edge detection.
Okay. Any other aspects? So all of you can convey whoever.
So, what is the difference between image processing and computer vision?
Okay, fine, good. What else?
So we started with the definition of image, then went ahead with distinguish between image processing and computer vision. And there, while dealing with computer vision, we dealt with template matching, the window technique and all.
Very good. So we started with the definition of image and went to the inference on the image from the image. Okay, and while doing such inferences, you may need to perform the identification of the object, and for that you need template matching. Good. Okay, what else did we discuss? Any other aspects that we have discussed in the last class? We also have differentiated between different courses that are on similar lines: computer vision, machine learning, deep learning, and artificial intelligence and other things. Okay, so let's resume our discussion. So as we discussed in the previous class, the task of computer vision is trying to make an inference, or the attempt to make an inference from images. Okay, and this helps in automation. And for performing the inference from images, you need both image processing, okay, some kind of extracting the attributes of the object to make better inference. That is in terms of feature extraction, and subsequently having an algorithm which not just makes the inference, but also has the learning in it, and hence does the inference very quickly in new scenarios. Such a learning based algorithm can be from machine learning, and it can be a classification algorithm for some particular tasks, like primitive tasks like classifying into different classes. So we have discussed with an example of fish classification. So we wanted to classify the fishes coming on the conveyor belt into two classes. And we said that we start with initially identifying or segmenting each different fish. That comes under pre-processing. Subsequently, we may need to perform the feature extraction for each of the individual fishes. And before that, we have to align them itself along a single direction to find out the attributes better. So that's also comes under pre-processing. After that, the feature extraction, like the length, width, average intensity, number of fins, and so on. Okay, that comes under the feature extraction. Subsequently, we should have an elegant algorithm that takes care of putting or classifying based on features into one of the category. That algorithm has to have a learning component, in the sense that if we have, say, if we have seen large number of samples, and we should benefit from them, in the sense that we should be able to use the knowledge that we already from the already seen samples, or to classify the unknown samples or the unseen samples. Okay, that's how that kind of learning ability has to be there in the algorithm. Okay, that's essentially where the machine learning plays a role in developing the pattern classification methods. Okay, so to distinguish the similar terms or courses, so this is a overall details. So signal processing, as you know, deals with the input being a signal that mostly is generated from a natural phenomena or a natural system, and it has a sequence in it. And it also has a, because it carries the information of the system, and hence its inference also is of great importance. Okay, so for inferring that, signal processing essentially does either in the time domain or in the frequency domain and so on, and the input and output essentially are mostly signals. Let that be a single one-dimensional signal or two-dimensional signal and three-dimensional signal and so on. Is there any example for three-dimensional signal? So here we may not strictly distinguish. Is it coming from a pure natural system or from a man-made system like cameras and so on? Okay.
Videos.
Yeah, video essentially can be considered as a three-dimensional signal because you have actually each frame is in two dimension. As we said, the image is a two-dimensional matrix, and then these are two-dimensional signal. And if we take 30 frames per second from a camera, and we have actually along the temporal direction as well. Okay, the two-dimensional signals coming up, that can be considered as a three-dimensional signal and so on. Okay, so these, see the signal usually well processing, the vector dimension is different and the dimension in which we view or represent the signal is different. Okay, don't get confused with say two-dimensional vector versus two-dimensional signal. Okay, or the vector can be of 100 dimension, 1000 dimension or whatever, right? But we are now considering about the spatial or the representation dimensions, not the number of elements. Okay, so subsequently in image processing also we perform processing the images, input being image and output being an image, and inference can be made by subsequent systems. And in computer vision, the main objective is to make inference from images or from videos. Okay, and hence the task of learning comes, the task of feature extraction comes. So the main aspect that has been dealt in computer vision, okay, since 1960s very actively is on feature extraction. Because if we have an image, for a computer, it's just a matrix or the set of numbers or two-dimensional set of numbers. And we need to make all information, what objects they are, how many objects they are, okay, and where they are, all such information from the image itself or from the video itself. That needs the effective, not just localization of the objects, even for localization of the objects, and after the localization of the objects, for better inference, you need the feature extraction or the attribute information of each of the parts of the image or each of the part of the object. Okay, so for that we essentially use some kind of feature extraction methods, develop some feature extraction methods which will give the features that are invariant to rotation, invariant to scale and so on. As you have seen in the previous example, if you would like to find out the count the total number of edges here, we have to have some features which are invariant to rotation, right? Otherwise you have to, when you make template matching, what you need to do? You need to make template matching for all the rotations. Okay, as we have seen, and all the pixels are all the locations and at all rotations. Okay, and it's exhaustive. So in computer vision, methods have come up without exhaustively making the search for the template. Is there a better way of extracting features itself that are invariant to rotation? Can I extract features invariant, say, let it be 0 degrees oriented or 90 degrees oriented or 45 degrees oriented or whatever? Can we have a same set of features for that object? Can I, in some sense, normalize the rotation and extract the features? Okay. Some such methods have been developed. And also see, you can see the illumination variations also can come into picture. We will see subsequently that the real world samples are very varying in terms of intensities, in terms of the views. Okay, the face view can be different. When we just want to recognize a face, the view also matters. For any 3D object, view matters. Okay, and then the scale also matters. So all these things, how do we essentially have features invariant to geometric invariant to geometric features, aspects, as well as photometric aspects. Photometric aspects being the intensities, okay, and then the contrast. Sometimes the contrast may be good, sometimes it may be bad, and so on. Contrast means the minimum to maximum difference, okay, of the intensities in a given image. That's referred to as contrast. The intensities in general can be in the lower intensity range, 0 to 50 range, or they can be in the higher intensity range, 200 to 250 range. Okay, so how to take care of all these aspects and have features that are invariant to these things for better inference. Okay, that's all being done in computer vision. So computer vision is also a independent or like has a very evolved field in terms of feature extraction. And the machine learning plays a core role along with the computer vision or along with the feature extraction to make the recognition or inference possible better in even from images or from videos. So pattern recognition, if we consider, there is a classical subject of the before evolving the term machine learning or wide application of the term machine learning, use of the courses on machine learning. Pattern classification and pattern recognition is the well-known subject that deals with recognizing the objects and recognizing the or developing the classification methodologies for putting the objects into different classes or putting each patch into different objects and so on. Okay, so that deals that further the input can be any data, not necessarily image data. It can be text data. Okay, like we do in Google search. Okay, we may want to match, okay, at the text level, and we may want to match at the image level or signal level, even say EEG classification, ECG based classification, all those aspects. Let it be in medical domain, let it be in computer vision domain, whatever domain, it doesn't matter. Pattern classification essentially does, it tries to classify the signals or the images, patches, or whatever content we give or data into different categories. Would like to put into different categories. Putting this data into different categories not just has the application in object classification or image classification, it has the impact in many other computer vision tasks. We will see subsequently. See, if I want to locate where the object is. See, my objective is not to find out what the object is or put into two classes, but I want to just find where the fish is, or just I want to find where the face is, okay, in a given image. So then what I have to do, what we do is we take each patch and try to see for the features. Say if I want to identify where the face is, take each patch and try to see where the features corresponding to the face are. Okay, so we keep doing that at each location. So that essentially is nothing but classifying each patch face or not face. Okay, so many of the, say this is the object detection or face detection, which is not a face classification problem, but still we can pose this as face non-face classification problem. Similarly, razor non-razor here, fish non-fish here, and so on. So like that. So we will see subsequently the many of the computer vision tasks that we have discussed briefly in the last class, like visual tracking, okay, and then object detection and many other tasks can be posed as classification problems. Okay, and hence the pattern classification and pattern recognition became a very important field, and computer science is the major domain with which it has originated. But computer vision and pattern classification has the very nice intersection or the applications together to have the better inference from images and videos. Okay, and then subsequently what people identified or recognized is in these classification algorithms or in these object detection or whatever recognition algorithms, the learning is very main aspect. Like in humans, we may not keep seeing the examples or like we don't feel or don't consider every problem as a new problem. Okay, we might have already learned from experience. Here, the computer algorithm might have learned from the data. That means the data of class 1, class 2, class 3 separately if we provide and say that this is from class 1 samples, class 2 samples and class 3 samples, and then say that we need to develop an algorithm that has the information of all this data, okay, in some sense in it, to separate these into different classes. The objective we may specify very clearly. Based on objective, there may be some objective criterion or an error function with which we train the algorithm, or we direct the parameters of the algorithm. Okay, and that will enable us learning in the algorithm. That is referred to as machine learning. Even for machine learning, the data can be 1 dimension, 2 dimension, or whatever dimension. Okay, it's essentially the data as the input. And what's its job? To make the inference. And it has to compactly represent the whole information of the data in an algorithm. Okay, through learning. That's essentially the role of machine learning algorithms. That learning, when it comes through a layered, deep layer structure or several layer structure, okay, that is referred to as deep learning. Okay, essentially in machine learning algorithms, they are shallow, referred to as shallow in the sense that the number of parameters are less, the number of layers in which it learns is less. Okay, if we learn primitive information and then subsequently finer information and subsequently finer information and so on, okay, that is essentially layered structure for learning. Such learning is essentially being done in deep learning. So whatever we do essentially in shallow learning, or essentially in neural networks, which I will introduce a little later. So in such kind of algorithms where we learn with a typically small number of layers to scale up to very large number of layers, there will be several difficulties. Okay, and there need to be some ability to capture the information of the data as it is for effective learning. So that is essentially dealt in deep learning. Not only that, as we discussed before, in computer vision, the focus was mainly on the feature extraction part. Okay, and the machine learning or the pattern recognition is mainly developed on the classification algorithms part. Okay, so both are very important for performing an autonomous or automation of any task. Let it be a visual task, or let it be a signal processing based task, or let it be any other task. For many tasks for automation, what are essential are, say, initially pre-processing or data processing and bringing the data or the signal to a particular format in which subsequently it helps us for better feature extraction. Okay, and feature extraction is essentially developed, as I said, through computer vision for images and videos to extract features which are invariant to shape, invariant to rotation, invariant to view, invariant to like intensities and so on. Also invariant to scale and so on. All such aspect effective feature extraction driven by mostly by the object properties, driven by shape properties, and that is the feature extraction. After that, the classification methods, which are mainly developed in pattern classification and pattern recognition, and as well as in machine learning based methods. So these three forms the core for any automation task or inference task from data or images. And deep learning has the ability to perform all of them together directly from the data to a greater extent. The feature extraction classification can effectively be done or through a learning process itself. Previously, as we discussed, feature extraction is different. Okay, that is dealt in computer vision or in mainly from the signal processing perspective, and classification is done mainly from the mathematical algorithmic development perspectives. Okay, and both together will provide us an inference or an automation for the system. Now, deep learning has an ability to have a feature extraction and classification together in learning process. Okay, we will see that. And artificial, as I said, is an umbrella in which the term artificial intelligence is coined in such a way that, okay, whatever you do with intelligence, you can put it under that. Okay, but essentially it has started with the rule-based methods and so on. Now, the core of artificial intelligence are the buzzwords that make artificial intelligence famous is the machine learning and the deep learning, more on deep learning, and applications of deep learning in computer vision more further to be focused on. So as we discussed, this is the evaluation criteria. So we may consider, as I said, 20% for programming assignments or tests or 20% for mini project. So based on assuming that, okay, students, all of you spend reasonable time on programming assignments and class tests, Now I have put 20% for this and 15% for the mini project. And quiz 1, quiz 2 for 15%, and final exam for 35%. If you have any like suggestions or the recommendations on this, you can mention on to me. So now what we do is we will discuss some of the we will like with depictions or with some examples. We will try to see some of the computer vision tasks, and we will try to see understand the complexity or the essential aspects or the background that is required to perform such tasks, so that it gives you a ground on with which you can, or motivation for studying this subject on machine learning, deep learning for computer vision. So far, any questions from students? Okay.
Sir, the approximate date for the quiz, can you tell us?
Okay. So date you can see in the calendar, academic calendar.
Yes, sir.
Yeah, that's all.
Okay.
That will be the date. Yeah. Okay. Any other questions?
For project, is it an individual or group project, sir?
Yeah, I would suggest it encourage for individual projects, and 2 students can be together for a project. So not more than 2 I encourage for a project. So 1 or 2 students, or 2 students, it's fine. Not more than 2 for a project. And for project, we shortly give some of the topics wherein you can start looking at and exploring for the understanding related aspects. But what usually happens is I will start with some of the basics, and then I will move on to the, as I will discuss the flow of the course subsequently in this class mostly. So by the time I discuss on the convolution neural networks and thoroughly with the convolution neural networks with applications, it will take some time. So those who wish to apply and develop the methods, they can parallelly pursue on understanding only related aspects for your project area, and then keep going on it. Okay, any other questions? Fine. So now let us see some of the applications. So what I will do is I will keep flashing some of the applications here. Okay, and then let's see the complexity or the background necessary for performing that application. Say, assume that if you would like to perform this, this is referred to as optical character recognition. This is very well known to you, and you might have noticed in many like in computers and so on, performing this. So Google also does this. So now the character recognition can also be done for the letters. So, and it can also be done for the handwritten characters and so on. So for this, what essentially is required? Can one of you comment on? What is the complexity involved in doing this? Okay. Shape. Okay.
Complex shapes.
Okay. Everyone will write in different manner. Where essentially when we do with say handwritten characters, okay, each will have a difficulty. So in learning corresponding things. Okay. And for this, essentially what kind of aspects that are necessary is to extract some kind of features for each of the digits or each of the letters. Okay, and then using those features, develop a classification algorithm to classify them. Okay, and this is iris recognition. See, many of the biometrics help for uniquely identifying humans, fingerprint, iris, and face also. So there are several biometrics which will help us to identify. So this is one of the biometric which will help irrespective of the age to identify a person. Similarly, we can perform object detection. So this is say identifying the object where it is and so on. This can be done in different, this has a spin-off applications in many ways. And this is again a biometric based recognition as we discussed just now. And these you may be very familiar. See, the complexity involved in each of them are different. So for example, if I want to develop an iris based recognition system versus a fingerprint based recognition system or versus a face based recognition system, what are the features that I need to extract? Can one of you comment on that, or can if you think of that any inputs on, so will all the three requires the same set of features or different set of features?
Different set.
Right? And what can you guess what kind of features are required for, say, face recognition, which is easy to start with? If I want to recognize, say, all, say we have all the students in the class, and I would like to give an automated attendance for the class. Okay, so how should I go about it? Any inputs or
Different-
comments on that?
Different angles of face,
Okay.
illumination, rotation,
Hmm.
and blocked by another face.
Okay. What should I do after all that? Yeah, please go ahead. What do we do with those?
We give names to each set of photos.
Right.
First, we give like correct answers for
So,
correct faces.
yeah, essentially what we do is we collect the data set corresponding to each class of samples. Okay, so if we have 10 people to recognize, for each of the 10 people, we record their faces in different views, different possibilities that in real case they may appear, and in which they may appear. And we take the collected samples of each class as the training data, okay, and use them effectively to develop an algorithm that learns from these 10 classes how to separate these 10 classes, okay. And in one of the phase of these 10 people is given, which is not there in the training data set, it will be able to then subsequently classify or put into one of the category or recognize or give the attendance. So if the class has 30 or 40 students, we take the essentially we record the we take the pictures of faces of all these 40 students in different positions and different views and intensities and so on, scales and so on. Then we may develop a algorithm with this training data set to classify and then automatically mark the attendance. Okay, similarly for fingerprint, see, the kind of features required are quite different. So grooves, like ridges and all those, like the kind of where all these meet, okay, where these diverge, okay, such all, it's like the kind of features required from application to application differs. In fact, they differ very greatly. So that's one difficulty, especially in recognizing the objects. So feature extraction is application specific, and you can't put the same features for all applications. That's where the difficulty is. Even if it is from the images. See, the kind of features we need to do head classify for detecting the head is different from detecting the face. Okay, so, but however, the methodology in which we perform this can be somewhat similar. Okay, essentially, the after feature extraction, classification methods using these features are all similar in the sense that once you represent the object or the patch in the image with respect to features, these features can be used in a similar manner, okay, for developing the classification algorithm. So all classification algorithms can be developed independent of the feature extraction. That's where the feature extraction and the machine learning or pattern classification has fields have evolved independently.
Sir, can you repeat it? I didn't understand that feature extraction is independent of.
Right. See, what usually happens is, as I discussed, for fingerprint recognition, you need one set of features, right? Say fish classification, different set of features. Okay, and then for face recognition, different set of features. But if we want to, once I get the features, okay, and I want to develop a classification algorithm, these classification algorithms, okay, can be same for all these feature, for all these tasks. These can be irrespective of which features we are dealing with. the aim of classification algorithms is what? Given a set of features for class 1, class 2, class 3, and class 4 or of class 10, we want to demarcate them in some way such that, okay, all the features of class 1 lie here, all the features of class 2 lie here, or all the samples of class 3, okay, with corresponding features lie here, and so on. So we essentially want to draw boundaries for class 1 samples, class 2 samples, class 3 samples, and so on. That is the aim of classification algorithms. Okay, but if we, what features do we start with? They doesn't matter to classification algorithms. Of course, there are some algorithms which also try to see that based on the feature extraction, can we bring the features in a compact way or select the features further? Okay, or can we reduce the dimensions of the features and do with the simplified classification algorithms and so on. But even that stage of feature selection and feature extraction or feature dimensionality reduction is also dealt as an independent block. So if I see now any inference task, either from images, also from images now, the initial part is on the pre-processing in terms of how the data should be to present, to make a better inference. That pre-processing is independent of other tasks. Okay, to some extent, now they're all connected in some sense, but it can be made independent, okay, to a major extent. So pre-processing is independent. Once we do reasonable pre-processing and position the data in such a way that features or attributes can be extracted, the feature extraction part is application dependent. What about the feature extraction? What about the pre-processing task? Is it application dependent or not?
It is.
No, it is. Application, given the pre-processing task is application dependent. For speech, different feature pre-processing may be required. For images, different pre-processing. Even in images, say face recognition and fingerprint may need different pre-processing. And similarly, each application may require different pre-processing. Pre-processing, feature extraction, they are application dependent or the domain dependent. Whereas the classification algorithms can be developed irrespective of the previous like application. So in whatever application, you just bring the features in that particular application, then the classification algorithms will be able to perform good demarcation. The classification algorithms mainly aim for how to separate the given samples or features. That's all they will look at. Okay. So they have been developed parallelly in the sense that computer vision community more concentrated on developing the feature extraction, pre-processing, all those aspects. And then in fact, the image processing mainly deals with pre-processing, and computer vision deals with feature extraction. Machine learning and deep learning deals with the classification methods. Deep learning does deal with the feature extraction and the classification together. Okay, and sometimes if, deep learning also can deal with some kind of little bit of pre-processing. So, but essentially pre-processing.
Sir, if deep learning deals with feature extraction as well as classification, so what is the need of computer vision?
Yeah, right. So that's where actually the evaluation has happened in that way. So when in fact deep learning has is evolved just from 2012 or 2010s. Okay, before 2010 there is no envisaging on the deep learning. So the whole field is on like extracting better and better features through images and so on. And the machine learning methods were only able to take, if we provide better features, they will do better classification. But if we provide inferior features, which cannot be separated at all, whatever we do, then the machine learning method also fails to separate them. They have the capability to separate even non-separable data to some extent, but nevertheless, the feature extraction also plays a great role. So that's how the field has been evolved. Now, in 2010, when the deep learning has come, it has posed the feature extraction and classification as a learning task together, putting together. So there is now a great boom or the effect or the ability, like the boost of the accuracies and the applications of deep learning. But however, the deep learning has a disadvantage that most of the things like goes like a black box approach, wherein we will not be able to understand exactly what is that we are picking up. What exactly are we learning? So the performance may be fine, but will they work on a new scenarios? Will they work if there is a small variation that we create artificially? So there is a good evidence that they do fail as well. So there is an interest now. In fact, there has been an interest to see how the very good interpretability of the computer vision and signal processing can be brought into the deep learning algorithms in terms of making them more understandable, or they get guided by a domain driven knowledge and also has the ability of learning. So there is no question of having no role for like machine learning or the image processing or computer vision. However, there is a currently, if we see the performance boost due to deep learning are much ahead. However, the importance of making it even to bring it even better or to bring it more understandable, you need all the knowledge of the computer vision as well as the machine learning as well, or image processing.
Okay, sir.
Yeah. So, of course, even the way we pose the problem of is being evolved from the computer vision. That means, see, all the computer vision tasks, as we discuss object detection, classification, and then tracking, and many other tasks that I will introduce, are not dealt in a similar way. Each has their own variations. And the way in which we deal the feature extraction in images plays a great role in developing the algorithms itself. So what is now happening is, without independently going about the machine learning and the image processing or computer vision fields, the deep learning is a field where the code development, the whole information of computer vision is embedded in learning, okay, in machine learning kind of. So there is a coherent developments that are happening to make the things better. Okay, so as I discussed, for especially in feature extraction, for different kinds of data, we need different kind of features. So that's where the difficulty in terms of the feature extraction comes, and the pattern classification courses doesn't much discuss about the feature extraction at all, because that's usually considered as a application dependent topic, and each application has to have its own methods, and they themselves are by subjects. For speech processing, you need a separate way in our speech feature extraction or speech recognition, which gets guided by speech feature extraction. You need a separate treatment, okay, or the separate kind of set of methods to be learned. Okay, so that's all done in a speech recognition or speech course. Okay, whereas image processing course is dealt differently, where image, how do we handle, what features do we extract, or how do we enhance or the pre-process the image as well. Computer vision, where the object information without irrespective of geometric and photometric variations, how do we capture the object information? That's all dealt in computer vision. So that has been like that. So that's why actually even now machine learning, if you see machine learning for signal processing, machine learning image processing, and machine learning or machine learning for image processing, computer vision and deep learning. So the subjects are also like this now, given that the application or domain dependent aspects are slightly different, or they have been evolved in a elegant way, and the advantage of current machine learning and deep learning are also to be taken care for making the methods better. So that's the background. The features are important, as we said, because the way, how do we represent the data to these classification algorithms makes a great difference. See, if I want to classify bikes versus cars, okay, if I give a set of pixels and try to say that if I give only these 2 pixels, and then I want to demarcate the motorbikes and non-bikes, do you think is it possible? It's not possible, because just 2 intensity. So if I give say pixel 1, what is the intensity? Pixel 2, what is the intensity? So if I sketch them, the samples are like this. So each of these points are nothing but samples with this intensity and with this intensity. If I have for a bike, for a one image, Okay, that I maybe for bike image. And if I have the another image wherein the in pixel 1 intensity is like this, pixel 2 intensity is this much. Okay, each sample represents a data point here when we plot them. So now it is not easy to separate the class samples of motorbikes and non-bikes. Okay, whereas if I compute some kind of features like wheels, having wheels and handles, number of wheels and number of handles, okay, then I may be able to say that the handles, okay, number of handles are more or one, for example, or number of handles are, so there is no handle, or the number of wheels, 2 or more. Based on that, if I classify, then I may be able to better classify. So this is to indicate that the classification algorithms, when we want to perform classification, the pixel intensities which directly occur in images may not be very good features all the time. So you may need to go for features which will describe or separate the samples better when we want to perform a classification task. Okay, so if you make the feature extraction very elegant, you need very simple classification algorithm. Okay, that has been very well proved in machine learning. Even in deep learning, that kind of aspects are now evolving, in the sense that, so if we make a very effective feature extraction, whatever may be the domain, let it be image, computer vision, or it be speech or whatever, if we make an elegant feature extraction or elegant description of the data, will that help in better learning or quicker learning? So that even the learning may be on learning the better features from the features, okay, from the primitive features that we provide, but still the learning can be in a compact way or in a computationally efficient way. So the feature extraction is also plays or the way we describe the image or the information in the image also makes a great importance. So as I mentioned, there has been a quite focus in computer vision to describe the features of the image. One of the very celebrated method in such describing the image content is using the angle of edges at each location. See, for example, if I want to describe this person, I want to classify person versus non-person. That means I am given some 100 images. I want to classify in these images person is there or not there. Okay, so assume that in 50 or 45 images the persons are there and other 55 persons are not there. So we want to classify each of the images having a person or not a person. So what essentially I need to do for this? I need to have a feature extraction mechanism that describes the features of a person. So what are the good features of a person? So what do you think of good features to describe a person in an image? Can some of you comment before I give clear details on this?
The shape of the body.
Okay, very good. The shape of the body. The question next is, how do we get the shape of the body?
Edges. Through
Okay,
edges.
edges. Fine, good. So edges are good. So how do I capture the edges? Say finding edges is fine, but I want to represent the image content in a nice way, right? So I have edges all across. The person may be, say, at any location in the image. Person may be here, person may be here. Okay, because camera is, okay, not like always positioned in a proper way. Okay, and person can be like sometimes like this. Okay, person can be sitting, person can be standing, all those aspects. Okay, and you may see from any view and so on. So now how do I make a representation of it? You're able to see edges in an image, and after looking at the edges in the image, human or visual interpretation is helping you to tell that it's a person. But we don't want to use human anywhere. We just want to make an automated task of recognizing or identifying a person or non-person, not a person. So I need to give a vector to all machine learning algorithms. So one more important point I will highlight again later is that all machine learning algorithms takes only one-dimensional input as input. Okay, that puts a very strong bottleneck for describing the image, like image content, because images are all two-dimensional, the objects are all two-dimensional in images. And in say if we make a video, it's like it's again each frame object has 2 dimensions. So giving always the necessity or the constraint to give in only one-dimensional vector as input to the machine learning algorithms puts a very strong limitation because all the spatial content is lost. Okay, so the deep learning methods does have a very good edge there in terms of directly putting the data in its own format. Let it be 2-dimensional or 3-dimensional or more dimensions. Okay, so now let's try to get back to our problem of how do we represent the edges now. Edges are fine, then I have to give it to the computer. So should I make a one-dimensional like the raster scan in the sense that all first row followed by second row, third row, and so on after finding edges, and then may stack them and put as a big vector 100 cross 100 image will become 10 power 4 cross 1 vector. Is that the suggestion you are giving? Or how should I represent the edges is the next question. How far in terms of a vector to give it as an input to a classification algorithm or a machine learning algorithm. Okay, so how people does this? See, there is one thing in image processing called histogram. Histogram, what it does, those who know about a little bit of image processing may know histogram. So what histogram does is, see, if in usually image content, as I said, it's from 0 to 255. At any pixel, you may have 0 or 65 or 125 or whatever. Now, if I see the distribution of intensities or the distribution of pixels with different intensities, what happens? X-axis is now 0, 1 and up to 255. The number of pixels having 0, number of pixels having 1, number of pixels having 25, number of pixels having 125, all that I will plot in the y-axis. So what initially I am doing, frequency of having the pixels with that particular intensity I am plotting as the y-axis. So it essentially gives me what? So the intensity distribution. Okay, that means how many pixels in this image has a particular intensity value. Okay, and this essentially gives in some sense, if I normalize them by total number of pixels, okay, the y-axis, then the probability of the pixels taking the intensity value of 0, probability of pixels in this image having a intensity value of 125 and so on. Okay, that's referred to as histogram. So that histogram essentially describes the image as a vector. Okay, so you have actually the intensity distribution in terms of, say, for example, 0 to 255 dimension vector or 256 dimensional vector you have. Okay, where the value of vector is the number of times a intensity occurs in an image. Okay, that's essentially descriptive of the image in terms of a intensity distribution. Now, the shape information I want to capture. Okay, now tell me, given that this background of histogram is given to you, is there any like input from you or thought from you to describe the edge information better?
Sir, where there is a difference in histogram level, and
Okay.
give that pixel value as a vector.
Okay. Okay, but pixel value as a vector we won't be giving, right? So what essentially we do is, so we have actually see it when we will discuss subsequently. Hopefully you will know very clearly that later. So the edge information is obtained by gradient. So gradient information means what? The variation in intensity in x direction, because it's not a one-dimensional signal, it's a two-dimension. Gradient in x direction, gradient in y direction. Okay, so tan inverse of gradient in y direction by tan inverse of by x direction gradient. Okay, gy by gx, tan inverse of gy by gx. Okay, gradient in intensity variations will give us the angle of edge. Okay, and then the magnitude of edge is given by root of gx square plus gy square. Okay, so now the angle of edge and describes the shape of the object, because if it is like this or like this or like this is given by the angle of edge. Okay, that means intensity variations in x versus y, in which direction the intensity variation is there. Is it along x, y, or 45 degrees and so on is given by angle of edges. Okay, our angle of edge is nothing but the gradient information. Edge means what? Wherever the transition of intensity happens from high to low or low to high, that quantifying the transition of intensities is nothing but the edge. Okay, in an image. but that quantification has to be done along XY direction and along Y direction. Okay. So given all that, you will have the final information of the magnitude as well as the angle of the edges. So putting together, you have actually the edge information, but the angle of edge will give you the shape information. So now I want to compactly represent it. So what do? I take the angle of edges and I make the histogram of angle of edges. So most of the edges are, say, human means what? He will be vertical or say horizontal, assume that. Okay. So then what happens? There will be dominant direction, dominant angle will be around 0 degrees or 90 degrees. Okay. So based on that, you can say that it's human or not. Say first dominant is 90 degrees and then the second dominant is 0 degrees. Assume that. Okay, then or 45 degrees, 0 to 45 degrees. So then you can assume it's a human. So based on that, the histogram of angle of edges, orientation of edges. Okay, that is referred to as one of the HOG, histogram of orientation gradients. That's a very celebrated feature that helps us to encode the shape of the images or the objects in the images. Okay, so some such feature descriptors are developed. So I will discuss more on it a little later. So in each of these things, given that kind of features, the problems posed are many, like classifying the object or detecting the object. Where this, for example, where the face is, even for that I can use histogram of orientation gradients. Okay, where the hands are, I can use this and so on. See, the problems can be extended to video processing as well. So if you want to find out a particular object, say here the object is this. I want to find out the query image block. Where is that in the video now? Okay, so it's easily to extend the application of these algorithms not only to the image but also to the videos. And this can be developed under, as I said, the identification of a particular object can be done irrespective of the several variations in the image. Just to show some of the variations that may happen in image, the subsequent slides now will indicate the some of the natural degradations that may happen in images. So this is the contrast, poor contrast. So irrespective of contrast, how do we do? This is the say rotation, okay, or scale. The original query object, the template of the object is bigger, but the object is smaller in the image now. How do we do that? There is a rotation, there can be noise, okay, and so on. So this is one typical problem of computer vision. So identifying a particular object, where it is, okay, the object localization, identification of the object. And then the first problem that we have discussed is classification. Okay, how do we classify a particular object? Is it a face or whose face it is, whose fingerprint it is, okay, and what the object it is. So essentially these two will help us to identify the where and what, okay, in images essentially. So these are two basic applications in computer vision is focused on. So if you have any questions, you can ask now before I conclude or discuss the other applications.
Sir, what is this SIFT?
Okay, I will discuss on this.
Okay.
Yeah.
Sir, basically the histogram method, what we do is we just check the slopes and basically.
Right. We identify the angle of edges, okay, at each location. And then what we do is after identifying the angle of edges, we make for each, say we can make the histogram for the whole image on the angle of edges. See, if I make histogram of angles, many 0 degrees are there. Okay, in the object, what is the shape of the object? If I have a cell phone like this, okay, you can easily identify most of the angles at 0 and 90 means it's a kind of cell phone I can classify. Versus a face, okay, where the face will have all angles like that. So it is easy to distinguish the objects by the angle of edges, okay, histogram of angle of edges.
And I pass that histogram to the algorithm.
Right, classification algorithm, correct. So that they will be able to classify the say cell phone versus face, for example, if you would like to do like that.
But if we take different images, there will be different angles, right, sir? So how would it be able to identify then?
See, there are different ways in which people do. See here, that's way what they do is they take each small patch. Okay, they don't take the histogram of angles for the whole image. They may take each patch and then find out the histogram of angles. In that way, what happens is small rotations. If you are like this or like this. Okay, so if you take the whole image, see face region is and the hands region and the other regions were all covered. Or if we take the image with both of them, so you can't differentiate. So the information of the main object, which we would like to distinguish, may be matched with the other information of the other objects. So they take the patch, each patch, and then their histogram. Okay, and that they will concatenate. So histogram of angles in this patch, in this patch, in this patch, they concatenate as a big vector. Like that they give for classifying, assuming that the other object information is not like it will be at separate location and this will be separate location. And these are good enough, gives a good clue for classification. So there are different ways of doing it. The other way is just normalize. Before doing the feature extraction stage, apply good pre-processing stage where you position all the images with the way you align them or the segment the objects of interest and so on, and then only go for feature extraction.
Okay, sir. So basically, we are just discussing some problems that are occurring in computer vision right now.
Right. Okay, you're asking some question? Okay, any other questions?
Hello, sir.
Yeah.
Sir, in slide number 15, once again.
Yeah.
The bike problem. Sir, here the number of the number of wheels are 2 and handle is there. Where in case of bicycle also we have same, right? 2 wheels and
Right.
handle. Then how we can distinguish?
Right. So as I said, this is application to application dependent. See, if you would like to distinguish between bicycle and scooters, then you may need to go for other features. Okay, so bicycles will have a chain usually. Okay, and scooters doesn't have chain, right? So you need to pick. That's actually where the art of feature extraction and the feature engineering lies. Okay, what features you should pick such that you can easily classify. See, if I ask you to say that only 2 features or 1 feature you have to use, only 1 feature. To classify between this and like bicycles and scooters, what feature do you pick? So you can't pick obviously, as I said, wheels. Okay, of course, the size of wheels to some extent, if it helps, you can pick. Okay, but better features could be, say you may have an engine here and it may not have to have an engine. There you may have a chain. Okay, like that. So what feature you pick is also very important for classification. Okay.
Excuse me, sir.
Yeah, yes.
So when we were making the histogram of frequency and intensity, so you said something about normalization. What is
Right.
normalization and why we need to do that?
Okay. See, usually what happens is, the images may be of different sizes. Okay, so if I have a 100x100 image and I may have a 50x50 image and so on. Okay, the number of pixels in 50x50 image is different, 100x100 image is different. But still what I may wish to have is I would like to see the content in terms of say, I don't want to take the absolute count. How many are at 0, how many are at 90? I wish to see that say normalized count. So in that case, normalization helps. Is that clear?
Yes, sir.
Yeah. Of course, normalization also helps in different other ways, because actually what may happen is you may wish to size is one thing, even scale also sometimes. Maybe like object appearing in different scales also maybe through normalization we can bring them to the same scale. Normalization can be on the histogram, also on the images or on the intensities. See, intensity sometimes what may happen is, as I said, 0 to 50 and then 150 to 200. Okay, the same image information may be at 2 different brightness values. So if I just bring all of them to 0 to 255 range, okay, that is referred to as histogram equalization. That is also a kind of contrast stretching or normalization. Through that, you can see all the objects in the same intensity ranges. Okay, and it's better to compare. Similar grounds for comparison, either in terms of the intensity normalization or in terms of the contrast stretching or in terms of the histogram value, like the magnitude normalization. Okay, any other questions? Okay then, thank you. So let's meet in the next class.